All right, so as I was saying, the image is formed here where the refracted rays, when traced backwards, cross at that point. And you'll notice something about the image. First of all, it's on the same side as the object. In this case, that makes this a virtual image. Image is reduced, and you'll also see it's upright. It's going to have a positive magnification. All right, well, what does that mean? That means that we can talk about the sign conventions for lenses in kind of the same way as for mirrors. For example, the focal length is going to be positive for a converging lens and negative for a diverging lens. Also, the object distance is going to be positive for a real object and negative for a virtual object. You know, you have a lens, you can locate the object on either side of the lens. It's not like a mirror where the object can only be on one side of the mirror. The object can be on either side of the lens. So what that means is if you flip your configuration around and always put the object on the left, then you can say it's a real object if it's on the left. Okay, now that's just a matter of convention, all right? That's just to keep things straight in my mind. You don't have to do that. But a virtual object can't exist if you just have one lens. When virtual objects become important is when you have multiple lenses and you have to solve the lens problem one lens at a time. And the image of one lens may be a virtual object to a second lens. This also allows you to keep straight then the image distance. For example, it's going to be positive for a real image. Okay, well, what does that mean? That means to the right. So you expect light to pass through a lens. So if the object is on one side, you know, you might expect the image to be on the other side. Potentially. Okay, then you can have a virtual, which is going to be to the left for a real object that's on the left. All right. Magnification then has a similar sign convention. Positive means non-inverted. Negative means inverted. So with this sign convention, we can talk about the lens equation, which turns out is also the mirror equation. It's handy that you just have one equation for both lenses and mirrors. So 1 over the object distance plus 1 over the image distance is equal to the 1 over the focal length. And the magnification equation is also the same. And this stands for height of the image and height of the object. So this is the size comparison here. Okay, so with this equation, or these equations, then we're ready to solve a problem or two. Now, it is possible for a lens to create a virtual image. Okay, for example, let's say that we have an object that is 7.10 centimeters, and it's going to be to the left. Okay, and this would be a diverging lens, and it has a focal length of 5.08 centimeters. Now, it's a diverging lens. If I were to tell you it's a diverging lens that has a focal length of 5.08 centimeters, it's up to you to know that that must be negative. Then the question becomes, what is the image distance? And we can solve that using the lens equation. 1 over dO plus 1 over dI equals 1 over F. So we're after dI, so 1 over dI is 1 over F minus 1 over dO, which is going to be 1 over negative 5.08 centimeters minus 1 over 7.10 centimeters, and that turns out to be minus 0.338 inverse centimeters. Now that's 1 over dI, so that's 1 over the image distance. So you need to solve for the image distance by taking the reciprocal of that, and it turns out to be minus 2.96 centimeters. Okay, and we can figure out the magnification as well. Magnification is minus di over do, so that's minus di, which is minus 2.96 centimeters divided by do, which is 7.10 centimeters, and that turns out to be 0.417. The units cancel here. So what can we see here? We can see the image distance is negative. That makes it a virtual image. It is also reduced, and the fact that it's positive here indicates that it's upright. So what we have is this case right here. We've got the diverging lens, we've got the object out here, and the image is going to form right there. It's going to be closer to the mirror than the closer to the lens than the object. It's going to be reduced, and it's going to be upright. All right, I'd like to give you a problem now so that you can work it. Let's say that we have an axis here, and we've got a lens that has a focal length, let's call that f1. And over here we have now a mirror that is concave that has a focal length of f2. And of course this has some focal point f1, and this has some focal point f2 as well. The focal lengths are probably going to be more important than the focal points, because focal points become important when we are doing ray tracing, but this is a problem. And let's say the distance between these two right here is 2 times f1 plus f2. And the object is out here. Okay, well the distance to the object is, let's say it's 2 f1 from this lens right here. And f1 is 6 centimeters, and f2 is 2.8 centimeters. Okay, now what could you find from this? One of the things you could find is the distance between the lens and the final image. Where is the final image? Because think about what's going to happen here. You've got light coming from the object that's going to pass through this lens, and it's going to form an image. That image then becomes the object for the mirror, and the mirror then forms an image itself. And the light from that image then passes through the lens again. So where is the final image? Where is the final image here? Okay, if you know that this is 6 and this is 2.8, and you know that the distance between the two is given by that right there, and you know the object distance, you should be able to figure that out. The way that you do it is one lens at a time. But you have 3 problems here. First problem is passing through this lens. Second problem is bouncing off of this mirror. The third problem is going through this lens again. I'll tell you the answers here, but I want you to work it and see if you can figure it out. The answer for what is the distance to the final image is it's 12 centimeters to the left of the lens. Okay, and what is its magnification? It's going to be -1. So this is the image distance, and it's inverted. Obviously it has a magnification of 1. Okay, so see if you can work this out and do it. I'm not going to do this problem. I want you to try to do this problem. I'll do another problem instead. So for this problem, let's say that we put things on a number line here. This is 0, and at some distance along this number line right here, we're going to locate a converging lens. This is going to be at the 36 centimeter point along the ruler here. And then down here, we're going to locate a diverging lens. Kind of poorly drawn, but that is at 66 centimeters. Okay, the focal length of this guy is 12 centimeters, and the focal length of the second lens is 6 centimeters. This one needs to be positive, but this one needs to be negative. Okay. The question is, where is the image? If the object is right down here at 0. And the distance to the object is 36 centimeters. Now it's to the left of the lens, so that needs to be positive. Focal length 1 is 12 centimeters. So I can solve this problem right here for the first lens. Now in this case, the object is going to form an image due to this lens here, and then that image becomes the object for the second lens. We don't have to worry about reflection going back through the lens because this is a lens itself, so light should potentially pass through. So wherever the image is formed here, we're done. Okay, so we're doing the first lens here. So this is for lens number 1. 1 over DO plus 1 over DI is equal to 1 over F1. And we're after DI. So what does that mean? 1 over DI is equal to 1 over F1 minus 1 over DO. And that's 1 over 12 centimeters minus 1 over 36 centimeters. You can work this out. Let me see what you get for an answer. For final answer, you end up with DI equal 18 centimeters. And it is to the right of lens 1. Now, it's to the right, so it's positive. It's to the right because we had a real object on the left, so it's to the right there. Okay, you got that. All right, now that image becomes the object for the second lens. Now it's 18 centimeters to the right, so it's over here somewhere, and the distance from here to there is 18 centimeters. So along our number line, if I'm working lens 2 right now, so let's do lens 2, the position for the object is going to be 36 plus 18 centimeters, and that's 54 centimeters. F2 is minus 6 centimeters. So what is the distance to the object? Okay. Now that's, I made a mistake. This is the position of the object, 36 plus 18 along the number line. So its position is 54 centimeters, but the object distance is this distance right here. That's D sub O. I made a mistake there. So D sub O is going to be 66 minus 54, or 12 centimeters? Yeah, 12 centimeters. Okay. So let's solve the, find the image distance. 1 over DI is equal to 1 over F2 minus 1 over DO. So that's going to be 1 over negative 6 centimeters minus 1 over 12 centimeters. And let me get that one. DI is negative 4 centimeters. Okay, now what does that mean? That means that the final image is to the left of lens 2. All right, so what is the final position then? It's to the left over here 4 centimeters, so there's 4 centimeters there. So what is that position then? Well, it's going to be 66 minus 4. So final image is at 66 minus 4, 62 centimeters. That's the position of the final image. All right. Okay, let's do magnification. We'll need to do that on a separate sheet. I'll just do it on the back here. Now, how do you get magnification? Well, magnification for the first one is minus di over its do, so it's going to be minus. Now, what was its di? Its di is 18 centimeters, and it's positive. So 18 centimeters divided by do, and the distance to the object was 36 centimeters. So that's a half. So it's going to be minus 0.5. Okay, the negative indicates that it's inverted and it is reduced. It's reduced by half its size. What if we did the same thing for magnification 2? That's minus di over its do. So that's going to be minus. Now let's see, its di was negative 4 centimeters. So negative 4 centimeters over do. Its do is 12 centimeters. Okay, so over 12 centimeters, so that's going to be 1/3, and it's going to be positive, so 0.333, so forth. So it's 1/3 of its original height. Okay, so now how do you get the total magnification here? Well, if this was 1 centimeter high, if the object were originally 1 centimeter high, it's going to be half a centimeter later. And then you take that half and you multiply it by this. So the total magnification is just going to be m1 times m2. So we're going to end up with minus 0.5 times 0.333. And that turns out to be minus 0.1667. And there you have the final magnification. So what do we know? The image is inverted, and it is reduced, and if the object was 5 centimeters height, that's its h sub o, that's its object height, then the final image is 5 centimeters times 0.1667, that's 0.833 centimeters in height. So the h sub I is 0.833 centimeters, and it's going to be inverted, but the inverted goes with the magnification, doesn't go with the height. The height is positive whether it's upside down or right side up. It's still the same height. So that's how high it would be, even though it would be inverted. Okay? All right, so we've done a problem. All right, we could do any number of problems here, but let's talk about lenses in real life. If you suffer from poor seeing, then typical poor seeing problems are either nearsightedness or farsightedness. What's going on in those cases is that the lens of your eye is literally changing its shape. As you age, your eye may grow, but the lens may grow at a slightly different rate, or it may warp, or there could be lots of problems here. If you are nearsighted, that means that you're sighted to see things near. You see nearby things clearly. That's called myopia, or if you have that, you are myopic. Okay? And that can be fixed. The opposite of nearsighted is, which means that you can see things far away, but you can't see things close up. And that's called being hyperopic. And as you age, even if you have good eyesight, as you age, you end up doing this. You end up needing reader glasses to see things up close. All right. Well, what's going on here is, let's say, here's your eyeball here. There is a lens up front here. There's your lens. And light enters through that. And then you have a detector back here. That's your retina. Okay, so light from a distant object, let's draw an axis here. Light from an object comes in, passes through, and is focused to a point back here somewhere. Okay, well, that's the way a perfect eye would work, is that it would focus right there on the retina. However, if you're nearsighted, what happens is rather than it focusing back there, it stops short of the retina and it doesn't reach, so those light rays continue on through like that, and you get the blurred image at the retina. So how do you fix that? Well, it occurs because the lens is focusing it too closely. So the rays coming in are focused too quickly. They need to be spread out more. So how do you spread things out? You add a diverging lens into the mix, and that way the rays that come in like this are diverted out just a little bit more, and then the lens of the eye can then correct that and focus it exactly where it needs to be. So you add a diverging lens to correct myopia. And the opposite would be if you were farsighted. Then what's going on in that case is that the lens would focus the light back behind the retina. The problem is the retina is up here, and you need to focus on that. So right here where the retina is, the light is not sharp, it's spread out. So how do you do that? Well, the light needs to converge more quickly. So you add a converging lens in, and then the converged light comes in and is able to focus at the retina there. Of course, true optometry is a lot more complicated than this, but this is a simplified view. There are a couple of optical instruments that you will probably encounter in your academic career, and that would be a microscope or a telescope. Let's talk about telescopes because those are cooler. Telescopes, the goal of a telescope is to do two things. It's to increase the angular size of an object. When you're looking at an object in the sky, you want it to look bigger. So it's to magnify the object. But it's also to act like a light bucket and to gather more light. So if you'll think about your eye, let's say this is your eye and you're looking up at the sky. So here's the lens, back here's the retina. Then this represents the size of the amount of light that can get through. So if light coming from some very distant object is coming through here, and if it focuses nicely back here, then you can't get much light through this opening. So the idea of a telescope is to have a bigger bucket. Maybe this is the diameter of the telescope here, and back here we can place like a concave mirror here, and then light coming in from a very distant object can now pass through this, and then if you have it focused to a point back here, maybe put an eyepiece back here, then your eye can look through there, and you effectively change the diameter of the iris that allows the light to come through to be this size. So that's the real purpose of a telescope. The real purpose of a telescope then is to gather more light, to have a bigger light bucket. And rather than allowing just this much light to come through, which is the size of your iris, it allows this much light to be gathered instead. Okay, but like I said, it's kind of a secondary concern to increase the angular size or the apparent diameter of an object, but that's a secondary thing. This is the primary thing. In fact, this is called a primary lens or mirror in this case. Telescopes can have lenses or mirrors. They can have lots of configurations. They can have a mixture of both. But let's say angular size. If you have something off in the distance, let's say this is an object off in the distance, it has some height h. And if it's some distance r away, it creates some angular size theta. Now you know that this is, if you imagine this as a big circle, then you can think of this height, especially for a small angle here, as just being some arc length s. like that, and S is equal to R times theta. So that's the arc length is equal to the radius times the angular size in radians. It has to be in radians. So theta is arc length divided by radius. This then is the theta here is the angular size. So the angle that you see here is going to be related to how far away the object is. So very distant objects are going to have very small angular sizes. Now, angular magnification, let's call that capital M. Angular magnification is equal to, let's say, some angular size of the final image divided by the angular size of the object. So this is... So we have the angular size of the image divided by the angular size of the object, and that is the angular magnification. So the purpose of a telescope is twofold. Number one, it's to increase angular magnification, and the second thing is to act like a light bucket. Now, as I said, there are multiple configurations of telescopes, but let's talk about a very simple type. Let's say we have an axis here, and we have a big lens up front. This is the primary lens. Okay, now something off at a distance here, if this is the center of the lens, has some angular theta. If we continue that on through, then it would go on through. This is the center of the lens, so that ray of light would go straight through. And then back here, we can put an ocular, which just means eyepiece. And the purpose of the ocular then is to take this object that forms an image back here. It has its own focal length. Let's draw a ray for it. And right there is where the image would be formed. And I should say that's the image for this primary lens, so let's call that I sub P. And then back here is where your eyeball would be, an image that you could then see here. You would actually be seeing this image here, but your lens would focus it to your retina back here. Okay, so here's the idea here. You have some focal length for this primary lens. Let's call that F sub O. The primary is sometimes called the objective. That's why the O is there. That's the focal length of the objective, divided by the focal length of the eyepiece. Now, these are images that are formed at the focal point of each of these. So this would be the image that's formed at the focal point of the objective here, and the eyepiece, it then takes that image as its object to form the other image on your eyeball back here. All right, so this is a focal length of the objective, this is a focal length of the eyepiece, and this would be the focal point of the system then. Okay, since S equals R theta, and theta is S over R, then this is the height of the image divided by R is going to be the focal length of the objective. So this theta here is the same as this theta here. And what is that? Well, here's the height of the image right here over the focal length of the objective. So that's this theta. Theta is equal to S, the arc length over the distance here. Okay. Now, theta then that's an approximately equal to, because we're treating this as if it is an arc when we know that that's a straight up and down 90 there. We're just treating it as if it's an arc. This would be then equal to approximately the height of the image over the focal length of the objective. All right, but for the eyepiece, we can do the same sort of thing. The theta for, let's call it theta prime, is going to be approximately equal to the height of its image over the focal length of that eyepiece. So if we take the magnification, it's theta prime over theta. That's going to be approximately equal to height of the image over the focal length of the eyepiece divided by height of the image over the focal length of the objective. And you see that the height goes away, and this is equal to minus the focal length of the objective divided by, so the focal length of the objective divided by focal length of the eyepiece. That's the magnification of a telescope right there. And then the length of the telescope is going to be equal to the focal length of the objective plus the focal length of the eyepiece. Now here's the point. Here's the point of this. I said there are two primary reasons you might want a telescope. One is to gather more light, and the second one is to increase the angular magnification. But here's the point. The eyepiece is something that you can change fairly easily. So if you change this f sub e, you can change the magnification. That means that any telescope, just by changing the eyepiece, you can change the magnification of it. So any magnification can be achieved by simply changing the eyepiece. What you cannot do is change the primary lens diameter without effectively buying a new telescope. So let's say I have a telescope that has a length of 1.25 meters. It's a long telescope. And the focal length of the eyepiece is 5 centimeters. That's 0.05 meters. Then the magnification is going to be minus focal length of the objective divided by focal length of the eyepiece. That's going to be minus L minus FE over FE. I know that negative sign made it back in there. So that's going to be 1.25 meters minus 0.05 meters divided by 0.05 meters. It's effectively 24 times. Okay, that's the angular magnification. Now, for a real telescope, if you were to go out and buy a real telescope, a magnification over 50 times is probably not worth it, because when you magnify the image, you're also magnifying the atmosphere, and that means that any turbulence that appears in the atmosphere is also going to appear in the image that you see. So a small telescope like the kind that you and I might be able to afford if we went to a store, 50, maybe up to 100 times would be okay. But here's the thing. If you go to buy a telescope, they will advertise this over the diameter of the telescope. But it is the diameter of the telescope that is the most important thing. So if you want to buy yourself a telescope for Christmas, then buy it based upon the diameter of the primary here, the diameter of the mirror or lens, whichever it happens to be, and not based upon the magnification, because you can make your telescope any magnification you want just by buying a different eyepiece. And you can see having a small focal length eyepiece increases the magnitude even more, magnification even more. Okay, that's all that I have to say about these things. I believe we are done.